Welcome back, guys, and I do hope you and your family are keeping well. So what we're going to look at today is a development of the work we've done on energy and energy transfers. We're going to look very specifically at gravitational potential energy. Okay, so you might remember that gravitational potential energy is the one that some kids or younger kids call uphill energy. Yeah, the energy that something has when it's high up, when it's moved away from the Earth, when it's lifted. Okay, so there's a little bit that we need to know about this. I'm going to talk about how it gets that gravitational potential energy, and what I want to home in on today for the GCSE is how you would calculate how much gravitational potential energy something has. So, to kick off with, okay, I've got two engineering nuts here, and if I give them gravitational potential energy, I obviously kind of lift them up, yeah? I lift them higher. I'm doing work against the gravitational field, the gravitational force in my laboratory. Now, if I was on the moon, remember, there is gravity on the moon. Neil Armstrong didn't fall off it. Okay, he jumped up and landed again. Okay, on the moon there's gravity. But if I lifted these on the moon, it would be easier to do because I would have to do less work to lift them. In other words, I would have a smaller force to lift them because up here they wouldn't have as much energy as they have on Earth. Okay, on Earth, gravity, the pull of gravity is stronger, so I have to feed in more energy to get it to this height. So we talked there about doing work, and you might remember, it doesn't matter if you don't at this stage, that work is force times distance. So if I do work on this, give it energy, give it gravitational potential energy, I put a force on it and I move that force through a distance. That's why you do less work when you lift something this high on the moon, because you use less force to lift it through that distance. So let's home in now on gravitational potential energy. Okay, gravitational potential. So when you put something up in the air, okay, it has the potential to fall. It has the ability to fall. It has in it energy that's stored inside it. Okay, and if it's lifted up away from the Earth, we call that gravitational potential energy. Okay. Now, what I wanted to look at for the GCSE is if I lift the little light nut up a distance, so we say 20 centimetres, and I lift the heavy one up 20 centimetres, I've moved them through the same distance, 0.2 metres. It's got to be in metres, hasn't it? Okay. But I've used a bigger force to lift the bigger one, the heavier one. They're the same material, so they're the same density. Okay, so I've had to do more work to get this one to here than the little one, to get it to the same height. Okay, so what we're saying there is we need to do work. We need to transfer energy to something if we're going to give it gravitational potential energy. And we're going to do that by lifting it. And if it's heavier, and what I mean by that more correctly is if it's got more atoms, okay, then we're not going to have to lift, here it is, a small number of atoms. We're going to have to give more atoms energy. So to lift this one through a height, and it takes more energy than lifting the little light one. There are less atoms to give energy to. Now, why have I banged on about that? Well, number of atoms in something doesn't change, never mind where you take it around the universe. Okay, so the number of atoms in this, the amount of atoms in this, its mass stays the same, whether I have it here in deep space or I have it on the moon. Okay, and this one, obviously, the number of atoms in this, its mass stays the same. So this might be 100 grams, kilograms, 0.1 kilograms. And this might be 1 kilogram of atoms. Okay, I'm not saying those are the actual values, but I'm just sort of kind of guessing for the demonstration today. So it's harder to lift this one to the same height as that one because it's got more mass, more atoms. But hang on, what happens if it's going to go out of frame, isn't it? If I lift it up here, okay, now I'm having to lift these atoms this high. and this high. So I'm having to give them double the amount of energy. I'm having to do twice as much work. Same force, but I'm moving it through twice the distance. Okay, so I've done twice as much work. So it's got twice as much gravitational potential energy if I lift it twice as high on Earth. So, a lot of talking from me. Perhaps you could pause the video and have another quick look at that and think about all the things that I mentioned. But to carry on, the main points I was making was, okay, that if you give something gravitational potential energy, you have to lift it and you have to do a force through a distance. You have to do work, okay? But the bit I was trying to home in on is the amount of gravitational potential energy that something gets depends on two things to start off with, okay? It depends on how much mass you've got, okay? So this has got more energy now than the little one. And the vertical height that you lift it through, okay? So this one, this is a weird example. If I lift it a very small distance and I lift the little one a huge distance, I think the little one might have more energy because it's very, very high. And the amount of energy that it gains depends upon its mass, which is small, but it also depends upon the vertical height. So, the amount of gravitational potential energy that something has depends upon its mass and the height you lift it through, and one other thing. It's easier to do on the moon. So it depends on how strong gravity is, the gravitational field strength. So let's go into deep space away from everything, galaxies, black holes, a lot, okay? And if I lift this in deep space, it's a really silly idea, okay? So I put it from here to here, okay? I actually don't give it any gravitational energy at all. It's not being pulled down, so I'm not working against the gravitational field because there isn't one. Okay, so to work out how much energy I've given it, none. I've got its mass, I've got the height that I've moved it through, and I'm going to multiply those two numbers together, and then I'm going to multiply by how strong the gravity is there, the gravitational field, which is naught. So the answer is going to come out as 0. I don't need to do any work at all. However, on the moon, if I lift this, okay, I've got a mass, yep. I've got a height and I've got the gravitational field strength on the moon. It'll be easier to do than on Earth. And I multiply the mass by the gravitational field strength by the vertical height, and that will tell me how much energy I put into it. So let's do the same on Earth. Okay, if we're on Earth and I lift it the same height as on the moon, okay, I've got the mass and I multiply that by the strength of gravity in my classroom, the gravitational field strength, about 10 newtons per kilogram, okay? And I multiply by the height. And I'm giving it more gravitational potential energy because it's harder to lift on Earth than it is on the moon. So, lots of kind of hand-waving experiments there. But you now know a bit about gravitational potential energy, and I hope you've got the idea that to calculate gravitational potential energy in joules, you need to multiply by the mass in kilograms, the gravitational field strength, G, in newtons per kilogram, and the vertical height in meters. Multiply M by G by H, and you will get the gravitational potential energy the item has gained in joules.
Super. Good. Fantastisch. Komm, guck hier hin, Perry. Ja. So machst du das. Ja. Guck mal, wo ist der Papa? Wo ist der Winke, Winke? Winke, Winke.
Okay, so let's have a look at gravitational potential energy a bit more mathematically. Okay, so we could abbreviate this to GPE, but in fact now we're a bit more advanced, so we're just going to abbreviate it to the energy, okay, that is potential. Okay, and for some reason at GCSE, whenever they write E subscript P, they mean potential energy that's the gravitational one. You don't need to do anything with that little letter, it's just there to remind us that this is gravitational potential energy. Okay, I might oscillate between the two, but it's easier to have one letter in an equation. This would be confusing. It looks like 3 multiplied together. Okay, so we have this sort of idea that if we have something we're going to lift up, so we're going to lift something up here, our little weight, okay, and we're going to lift it up high. The important thing is it's the height that we lift it through vertically, okay, so we can have a look at that height. So let's make this height 0.5 meters. Okay, now I purposefully done that in meters because in the exam they might do 50 centimeters. Okay, 50 centimeters, but we don't work in centimeters in physics, we work in meters, and the equations work in meters. So we've got a vertical height. Okay, so this thing ends up here, our weight. Okay, and let's say that this one has a mass of, let's say, 2 kilograms. Okay, so if they give it you in grams, you must convert it to kilograms. Now, there's one other thing we need to know, that we're on Earth. Okay, and we know what the strength of gravity is on Earth, the gravitational field strength. On Earth, G, the gravitational field strength, is approximately 10 newtons per kilogram. Okay, it's 9.81, and check when you do your GCSE what number you have to use. When I taught in Scotland, they were really particular that you used 9.81 and not 10. But for heaven's sake, you know, if you use 10, you're showing that you understand the physics, and it allows you to estimate in your head very quickly. So we said that the gravitational potential energy of something depends upon 3 things. It depends upon the mass of the object, it depends on the vertical height that you lift through, and it depends upon the gravitational field strength. Okay, and at this stage it gets really easy. Okay, to work out how much energy something has gained, the gravitational potential energy it gains, EP, so the GPE, is just very simply denoted by mgh. Okay, so if you want to know how much gravitational potential energy an object's gained, multiply its mass in kilograms, the gravitational field that you're operating in, so on the moon it would be much lower, it'd be a lower number. Okay. Oh, by the way, in outer space, away from galaxies and black holes, that would be 0, so you wouldn't need any energy to lift something up, and if you let go, it wouldn't fall back down again. Hasn't got any gravitational potential energy gained from your hand. So G is going to be measured in newtons per kilogram, which it always will be at GCSE. And finally, the height must be measured in meters, not centimeters. So let's do this one quickly. So I'll change colour. So the energy gained by this one, okay, the potential energy gained will be mgh. So the energy that this small object gains is equal to its mass, which is 2 kilograms, times the gravitational field strength, 10, times by the vertical height that we raise it through, 0.5. Okay, I've picked easy numbers, you can see why. Okay, so 0.5 times 10 is 5, and 2 times 5 is back to 10. So it's 10. Or 2 times 10 is 20, half 20 is 10. And my students will know, I'll go, we've made a mistake. What have we done wrong here? Units. 10 joules. Okay. So at GCSE, it could be all sorts of things being lifted, but if they're raised through a vertical height and you know their mass, okay, and you know the gravitational field strength, to calculate the gravitational potential energy that it has gained going up, it is mgh.